Hello, Calculus and Vectors class. This is 6.3 exponential functions, natural logarithms, and Euler's number. I will tell you right now, there's not very much calculus in this at all. This is mostly just a review lesson, just to kind of hopefully get a little bit less rusty on things like exponential functions and logarithms. I hope that all of you have seen logarithms before. If not, you're going to get a quick introduction and review in this lesson. So I'm going to speed through some of it, but I'll try and make sure that I spend enough time on the stuff that might potentially be either new to you or newer to you. So the first part, how does the function y equals 5 to the x compare to y equals 0.5 to the x? You notice that it is just kind of reflected in the y-axis. So a couple of things that you should notice is that they have the same y-intercept. And they also have no x-intercept. They have the same asymptote. They have different directions. And both of them are always concave up. So just by looking at them, we can tell that they're connected. And they have some similarities, some differences, but they are connected. Now we're going to take a look at a different pair. Now hopefully you've seen this letter E before. If not, it's called Euler's number. Leonhard Euler was a mathematician. He kind of created, he was the one that kind of discovered logarithms. And he has this number named after him, Euler's number. And in fact, there's actually an infinite limit that can be used to help figure out the number, but don't worry about that too much. The big thing to know is that his number is 2.71828 ... As long as you know 2.71, that's the big thing to know. And you'll notice that there's an E button on your calculator just in case you need it. Usually, instead of you typing 2.71 into your calculator, I just use that E button, and it makes life a lot easier. You may want to just test it and make sure that it works. If it doesn't, just make sure that you figure out how that works. So this is the function e to the x. It's an exponential function with that as the base. So we can rewrite that as y equals 2.71 ... to the power of x. Now this seems like a pretty kind of arbitrary number, but kind of like pi, it's very significant, and over the course of the next few lessons, you're probably going to see why that one is pretty significant, especially when it comes to calculus. You're going to see why that number is kind of significant. Now we're going to have this function, y equals the natural logarithm of x. Now, in fact, the other way that we can write that is the logarithm base e of x, or the logarithm base 2.71 ... of x. So you can already tell that these two should be kind of connected. We know, hopefully you remember from advanced functions, that exponential functions and logarithmic functions are connected. We can already see that there is a similarity in the shape. And the next page, usually when I teach this in class, I go through this in a bit more detail and we talk about it. But hopefully you'll notice a few similarities. You'll notice that the domain and the range, we just kind of swap them for each other. We notice that they're both increasing. And we notice that the intercepts are alternating. They'll both have the same asymptote. They both have the same, they have no maximum endpoints, they have no inflection changes, and one is concave up and concave down. And the big thing to take away from this is that these two functions are inverses. So make sure you remember that, because they are connected. And you're going to see that on the next page, how they are inverses as well. And I'll point that out when we get there. I'm not going to go through the next section. Essentially, all of this is a chance for you to get some practice calculating different operations with E and natural logarithms on your calculator. make sure that you punch these in and make sure and verify that you can get these same answers, because that'll be really important to doing the calculations correctly. But continuing on, here's the part that is probably either going to be new to you or something that's probably a bit newer. So we're going to go through these rules really quickly. When you see logarithmic functions and exponential functions, there are some rules that apply across the board. Rule number 1 says that if we have two numbers or two different things multiplied inside a logarithm, we can separate them into their own logarithms. So we just have log base b of x and log base b of y. Property 2 says that if those two things are divided, it works the same way, except instead of addition, we get subtraction. So this time, we separate them into their logarithms, but we subtract instead of add. So same as rule 1, but just that one little difference, subtracting instead of adding. For property 3, it says that if whatever we have inside the logarithm is raised to an exponent, we can actually just move it out the front and it ends up like that. So it's going to be n times the log base b of x. Property 4 says that if we have a logarithm base b of x, then we can just make a fraction out of that, and on top we're going to have the log base a of whatever's inside the logarithm and the log base a of the base. And don't worry about the a value. As it turns out, a can be anything, as long as it's the same base for both the logarithms. And the last rule, which kind of connects back to what we were talking on the last page, is that if we take e, the power of natural logarithm of x, it's equal to x, which we see up above. I don't know why I'm writing that. But what you should notice is that that's e to the x, and then we have natural logarithm of x. We said those are inverses. So it means that e and natural logarithm cancel each other out, and we're just left with that x, which we have here. And the same works in reverse. So it's almost a good analogy would be something like the square root of x squared. We know that those two are inverse operations. They cancel each other out, and we're left with just x. Same basic principle. So now that we reviewed those rules, let's try some exponential problems that apply, that we can use these. So let's try an example that will, sorry, it's a little bit late when I'm writing, when I'm doing this lesson. Let's try an example where we can apply some of those properties of exponential and logarithmic functions. So the population of a bacterial culture as a function of time is given by the equation P of t equals 200 times e to the 0.094 t, where p is the population after t days. So question 1 says, what is the initial population of the bacterial culture? We know just from our understanding of exponential functions that our a value up front is the initial value. But if we want to be a bit more concise about it and a bit more mathematical, we could say that it's going to be at t equals 0. So t equals 0 equals 200 times e to the 0.094 times 0, or 200 times e to the 0, which is 200 times 1, or 200 bacteria. So we're going to estimate the population after 3 days. So that's going to be t equals 3. So that's going to be the population. So p of 3. And that's going to be 200 times e to the 0.094 times 3, or 200 times e to the 0.282, which is equal to 200. That's going to be e to the 0.282, should be about 1.3258, or roughly 265 bacteria. Next question says, how long will the bacterial culture take to double its population? Well, we know the population is going to be P of t equals 200 times e to the 0.094 t. But this case, we don't know what t is, but we know that P of t is going to be, if we start with 200, then double the population is going to be 400. So we're going to plug in 400 for P of t. And we're going to try and solve this. So first, let's start by moving the 200 over. So let's divide both sides by 200. And we're left with 2 is equal to e to the 0.094 t. So next step, this one's going to seem like we're not really sure why, but unless you've dealt with logarithms before, hopefully you have. So you notice how we have base of e in our exponents. So what we're going to do to help get rid of this is we're going to take the logarithm of both sides, and we're going to take the logarithm base e, or the natural logarithm. So that's going to be the natural logarithm of 2 is equal to the natural logarithm of e to 0.094t. That probably seems like a bit of a silly thing to do, and maybe if you haven't seen this before, you might not be sure why. But take a look. We said that if we have inside the exponent we have it raised, or inside the logarithm we have it raised to an exponent, we can just move that exponent out front according to property 3. So what that means is for the right side, that exponent can just move out front, and that becomes the natural logarithm of 2 is equal to 0.094t times the natural logarithm of e. Now, natural logarithm of e, you can confirm on the calculator if you like, but we know that should be just 1. So that goes away, and we're left with natural logarithm of 2 is equal to 0.094t. So that's going to be natural logarithm of 2 over 0.094 is equal to t, or t equals 7.4 days. So it's going to take 7.4 days for this bacterial culture to double in its population. And lastly, question D is asking us to rewrite this function as an exponential function having base of 2. So let's start by writing out the function. So P of t is equal to 200 times e to the 0.094 t. So the next step, let's see. So now we have to rewrite e 0.094t as 2 to the power of something. So what we're going to do is we're going to take that e. We want to have something in here instead of e. So we're going to say that e is equal to 2 to the power of something. Let's call it a. So we want to figure out what that's going to be. And you'll see why in just a second. If we can get this as 2 to the power of something, then we have it an exponential function base 2. So let's see if we can find what that a value is to make this work. So in this case, I think we're going to have to take the log base 2 of, actually, you know, it doesn't really matter either way. Let's take the natural logarithm of e, because it will get rid of that e. So now that's going to be 1 on the left side, and natural logarithm of 2 to the a. The a can move out front, and we're left with a times natural log of 2, or a equals 1 over natural log of 2. So as it turns out, we can rewrite this as 200. And we said e is going to be equivalent to 2 to the power of 1 over natural log of 2, which we just found in that section on the right. And then that's going to be, we still have that 0.094t. So lastly, we just need to tidy that up a bit. That's going to be 200 times 2. And we're going to use the power of the power rule. We're going to multiply that 1 over natural log 2 with the 0.094t. And that's going to be 0.094t over natural logarithm of 2. So we could write it that way. Or if we really wanted, we could simplify that. We could say, we can calculate out the 0.094t over natural log of 2. And as it turns out, when you do that, it becomes t over 7.4, which kind of makes sense given that we just found that the doubling period is 7.4 days. Because now let's see, if t is 7.4 days, it means that that exponent, that's going to be 2 to the power of 1. If we have 14.8 days, that's going to be 2 doubling periods, so it's going to be 2 to the power of 2, and so on and so forth. So hopefully that helps a little bit. Like I said, this is not really the calculus stuff just yet, but it's important to have these skills down pat before you start trying to deal with differentiation, because these skills will come into play a fair bit. So make sure you do some practice, and I will see you in the next lesson.